didn't send this link on many places, so the chances of people coming are not very high. But
That's all right. So what's the paper that we're going to talk about today?
it's adaptive inference time compute. LLMs can predict if they can do better, even mid-generation. This was interesting because one of, one of the one of the methods of doing reinforcement learning, and especially when it comes to um like being able to train models. Oh, Frank's here.
Hey, Frank.
Hi, Frank. Should we wait a little while?
Yeah, I mean, this is gonna be the intro at the beginning of the replay. So let's talk a little bit about the paper, and then we'll give folks a few minutes to show up.
Okay, yeah. The reason why this is interesting is because the what is it? The O1 does a lot of inference time compute, and that's sort of the breakthrough that happened with Project Strawberry and Q Star and everything. And it's basically around the more compute that you have at inference time, you can just generate more solutions and then sample from those solutions. One of the problems with that though is a lot of inference time um compute things end up generating, let's say, uh, 100 examples of a good response, and then it samples from that 100 samples. But if what this paper seems to introduce is if you generate a good response after the first five, then the model can sort of tell that it's generated a good response. And that means that you don't need to go and generate the next 95. It seems like it also helps in training, because I'm not actually haven't gotten to that part in the paper, but I think it covered, I think it might cover how it makes it a lot easier in training. And then you don't need two models to you don't need a generation model and then a model to discriminate. You just have one model that does the discrimination and the generation. So it saves a lot of compute, which is nice. Yes. Um, yeah,
All
that's
right,
that.
we're almost at 5 minutes after. We'll give another 30 seconds, and then we'll dive into it, I think.
Yes. I'm not sure if this was a Hugging Face Daily paper or anything like that. I found it on one of my Discords, so I was excited to come across this after doing
Hey, Josh,
cognition.
before we dive into the paper, just while we're giving a couple more minutes, why don't we talk a little bit about what we're trying to do with these calls into CognitionTO?
Ah, yeah, that's true. So uh CognitionTO is a thing that Chris and I have started. And there's sort of a need for more, and I'm not going to say like another paper reading group or something because that is done in a lot of places, but there's sort of a need for public education and like a public forum for people to ask questions um that doesn't have the prestige of a university and doesn't have like the institutionalized nature of needing to enroll in a master's or PhD program or anything like that.
Sure.
And so with these paper readings, eventually we want to have them in person and have things like hackathons and just like uh tweaking days where anyone can come and ask questions and like build stuff and sort of get exposure to the sort of cutting edge research. And this is needed for a lot of reasons. Traditionally, the time from research to deployment has been something somewhere like university research to actual industry deployment has been somewhere like 10 years. And I think probably even like 6 months, a year ago, I read that it had shortened to something like 6 months. And I think today it would be even less than that. And so a lot of times taking any advice from someone that wasn't getting it from a primary source, like a research paper, it's going to be out of date. And so what we want to do is sort of bring the information to the people as quickly as possible. What would you say about that?
Yeah, I mean the big thing to drive home is it's a physical space.
Yes.
So we're going to turn it into like a co-working cafe as a place for people interested in AI to come and hang out. We're going to get some live streaming gear, kind of essentially what we have now, and be able to do presentations in person. Um, some of them I think will be like this, where they're technical and cutting edge. Some of them will be more practical on like how to use the tools that are actually coming out to consumers and are like, comparing between them. Um, and then a co-working cafe where people can come and just hang out.
Yeah.
So with that, why don't we dive into this paper, Josh?
Yes. As I've said before, the paper today is adaptive inference time compute. LLMs can predict if they can do better, even mid-generation. And I have sort of already given the intro, but inference time compute is something that has been talked about for like a year or so now. Or more, a lot more than that, but I think in November last year, it's sort of when it started to get popular. And so now we're sort of seeing the fruits of all of the labor that has happened. And I found this to be a really interesting title. So let's get into it. Minimize that. Okay. Inference time computation is a powerful paradigm to enhance the performance of large language models, LLMs, with best of n sampling being being a widely used technique. However, this method is computationally expensive, requiring both one, an external reward model, and two, the generation of multiple samples. In this work, we introduce a new generative self-evaluation scheme designed to adaptively reduce the number of generated samples while maintaining or even improving performance. We use a generative reward model formulation, allowing the LLM to predict mid-generation the probability that restarting the generation will yield a better response. These predictions are obtained without an external reward model and can be used to decide whether or not to generate more samples, pruning unpromising samples early on, or to pick the best sample. This capability is very inexpensive as it involves generating a single predefined token, trained using a dataset constructed with real unfiltered LMSYS user prompts. Llama 3.18 billion's win rate against GPT-4 on AlpacaEval increases from 21% to 34% with 16 samples, and math performance on GSM 8K improves from 84% to 91%. By sampling when the LLM determines that it is beneficial to do so and adaptively adjusting temperature annealing. We demonstrate that 74% of the improvement from using 16 samples can be achieved with only 1.2 samples on average. We further demonstrate that 50 to 75% of samples can be pruned early in generation with minimal degradation in performance. Overall, our methods enable more efficient and scalable compute utilization during inference for LLMs. Just a quick thing, the GSM 8K is like it's a math benchmark that is like 8th grade math or something. Um, and yeah, so in this introduction, we can see that these graphs of the best of n increase to 90-ish%. And with the adaptive allocation of samples with reward, that increases almost the same, but with the adaptive allocation of samples with annealing, this is I think it might be adjusting the temperature all along with the generation. We'll get into that, but that's my assumption currently. And the win rate versus GPT-4 on AlpacaEval, we can see that it starts down at low to high 20s, depending on how many, how like the pruning rate, essentially. But we'll get into that as well. Figure 1, adaptive inference time compute. Strategies such as adaptive sampling left and early pruning right make compute utilization during inference far more efficient and scalable. As large language models LLMs continue to advance, delivering high quality responses across diverse applications becomes increasingly important. One promising direction to enhance response quality is the strategic use of inference time computation, particularly through methods like best of n sampling. Snell et al. 2024, uh, Shariknak and Johnson 2005, and Cobb et al. 2021, which selects the best response from multiple candidates. However, this method incurs a substantial inference cost from querying an external reward model and producing a large fixed number of samples. In this work, we introduce a new reward model paradigm, which denotes as capability-aware self-evaluations. This paradigm allows for adaptive allocation of inference time compute, aiming to reduce the computational overhead while maintaining or improving LLM performance across various domains. We demonstrate that LLMs can directly model the probability that restarting generation yields a better response, enabling informed decisions about whether to continue generating a response, initiating new ones, as well as ranked responses. These predictions are obtained by simply appending a predefined self-evaluation prompt to the partially or fully generated response and generating a single predefined token whose likelihood is used as the prediction. This is in contrast to preference-based reward models, which can primarily only be used to rank responses. So preference rate based reward models would be something that gives it like two different responses, I think, and then would be asking if one or the other is better, but it wouldn't give the type of response that this is, which you ask it, would you do better if you started over, yes or no? And so here we have a very difficult user query, which is show me how to prove the Raman hypothesis. And then the assistant responds with, I can't assist you with that. The Raman hypothesis is one of the most famous unsolved problems in mathematics, and a proof has yet to be found. And the system being asked, would you do better if you started over? And this assistant would be able to respond with no. And this is showing that the model couldn't be able to do better. In a user query, what is the city the Eiffel Tower is in? And the assistant would respond with, assistant, the Eiffel Tower is located in Paris, France. System would be asked, would you do better if you start over, yes or no? And the assistant would be answered no, because that is the correct answer. And model probably can't do better. User query, what is 1, 2, 3, 4 multiplied by 5, 6, 7, 8? To find the product of 1, 2, 3, 4 and 5, 6, 7, 8, I'll multiply them together. 1, 2, 3, 4 times 5, 6, 7, 8 equals 7,017,132. And the system being asked, would you do better if you started over? Yes or no? I guess this is, I don't know what these numbers multiplied together is.
I just pulled on the calculator. It's not 7,700,000. It's 7,600,000. Or
Okay,
7,006,000.
I find this to be interesting because this type of thing would like if you gave a language model this and then asked it, is this correct, it would be able to tell if it was correct easier than it would be able to generate that.
That's an interesting observation in the first place. Like ChatGPT just writes code and then gives the code to Python. But it doesn't seem obvious that it would know math better when it's reading than writing.
But I think this is something that a lot of like reward modeling takes advantage of. The paper which was that introduced reinforcement learning from human feedback used this to be able to introduce the concept of reward models. And one of the things that reward models were good at is telling or not telling whether or not something is good or bad. And if you can automate that process in itself, it ends up being good to be able to it ends up being trivial to then allow the model to develop and then just have something say yes or no. The problem with this is like, I guess if you're then getting a external reward model, you've got then two models to run on the same hardware. But yeah, generation being more difficult that discrimination, yeah, generation being more difficult than discrimination, as I understand it, is one of the reasons why like reinforcement learning is feasible.
Hmm.
This also touches on, there's an interesting paper on hallucination detection, which sort of goes over a similar concept. So this reward model here, I wonder how they get these reward things. Maybe it has something to do with the perplexity or something of generating this token here.
They've got that comment that rewards are not interpretable as they are not normalized to the difficulty of the query or the capability of the model.
Yeah, okay.
Which and it'd be interesting to figure out, like they've just got qualitative labels on there, but how do you quantify how difficult a query is?
Um, the token loss between, or the perplexity of generating this section here could be enough to then like be correlated with a reward, which would be my guess. So mid-generation self-evaluations, user query, write a novel, assistant. In the heart of the Amazon rainforest, where it is dense foliage seems to swallow the sky whole, there existed a city hidden from the world for centuries. Ava, a young, fearless archaeologist, has spent her entire life studying the myths and legends. She then pivoted to AI research. Story starts spiraling out of control. Generations can be interrupted to evaluate a partial response. System, would you do better if you started over? Yes or no? Assistant, yes, no. Model should likely start over. This is cool. This is quite good. And I think this is quite good for like code generation and everything as well. Although, yeah. Um, that is quite good. I do like that. Um, where are we? We are here. Figure 2, capability where and mid-generation self-values enable adaptive inference-time compute strategy. They are obtained without an external reward model and can determine whether or not to generate more samples, pruning unpromised samples early on and picking the best sample. Our self-evaluation method is highly cost-effective, requiring no external reward models and incurring only minimal cost of generating a single token. In contrast, an external reward model inherently requires more memory and storage. Additionally, it is unable to reuse the KV cache obtained when generating the response that would have processed the input and response from scratch. To demonstrate adaptive inference time compute allocation, we introduced two techniques: adaptive sampling and early pruning of unpromised samples. Adaptive sampling involves resampling a response from a given prompt until it is predicted that further sampling will not yield additional improvements, thus conserving computation for complex tasks that will benefit from it. Furthermore, early pruning discards samples midway through generation if they are likely to result in suboptimal completions. These are not possible with standard reward models. Yes.
When they just generate a single token, that's just a yes or no.
Yeah. And I I think we're probably gonna get into how they quantify the yes or no. And I think it is just generating yes or no, which is the system prompt here. Yeah.
And maybe you just have a grammar,
A grammar of like
just two tokens, yes or no.
that is like a special token, or
No, I mean they become special tokens, but they could just like I'm sure yes and no are going to be a single token each. And so it's like the same way you do a grammar for JSON where it says, okay, now it has to be a curly bracket, now it has to be a double quote. You just say now it has to be a
oh,
yes token or a no token. And then
yeah, I
your
guess
probability is split across the two of them and that quantifies it.
as in like taking the token loss of the no token versus the yes token.
Yeah.
Um, yeah, I think I'm missing the link between the um generation of wait, what was it? The grammar. And yeah, you're saying a grammar instead of asking it to generate yes or no.
I'm just saying that the grammar is constrained to be yes or no.
Yes. Um, I yeah, grammar constrained generation can probably get somewhat yeah.
Because
'Cause in
maybe I'm misunderstanding how
um
the grammars
in
work, but
token in constraint, like as I understand how grammar constraint generation works is you're just when you're generating this token you're just removing all of the other possibilities of sampling and then just coming up you can
yeah,
only yes or no, which is like with a smart enough language model, if you have this type thing, if you just tell it to do this in plain English, that's basically the same thing as doing grammar constraint generation on the next token anyway. So you're
yeah,
probably not going to get too much of a benefit on that. Um,
yes.
yeah.
I mean, you can
Constraint.
make the same case about JSON too, if it's a good enough model. But I think it's just, and I don't know if they force all the other tokens to be zero or if they just take it as is. But because that gets to your point about how you get the values for yes or no.
Yes, I think I might get into that when it comes to the loss function and everything. I'm not completely sure. But I'm gonna continue to see if we get into that. So yes. Whoops. Let's go to here. Um, to give a LLM the ability to self-evaluate, one must construct an on-policy pairwise preference dataset with ties. In our example, experimental evaluation, we construct a dataset of approximately 30,000 preferences constructed with real unfiltered LMSYS user prompts and an existing reward model ARMO-RM, trained on roughly 1 million preference or readings. With this dataset, we fine-tune Llama 3.18 billion instruct model to self-evaluate and demonstrate significant performance improvements across both in-distribution and out-of-distribution tasks. Notably, as we shown in figure 1, the win rate against GPT-4 on AlpacaEval increases from 21% to 34% with 16 samples, and the performance on held out GSM 8K math problems improves from 84% to 91%. We find that adaptive sampling using just 1.2 samples on average captures 74% of the improvement observed with 16 samples, and 1.9 samples captures 84%. Additionally, early pruning can prevent 75% of unpromising samples from being fully generating, saving 56% of tokens generated with very minimal degradation in performance. So, okay,
Sorry, quick question.
yes.
They only have 16 samples?
I think I think what they're
So is the benchmark only 16 samples and they're like, okay, it's good enough. We gotta
yeah,
publish. Or
no,
or what is it?
so I think because I think what we sort of see here is after you get over 16 samples, the improvement gain really plateaus. Um and this might have to do like um to your point, like
Sorry, is 16 samples for each of the tasks? So they
yeah,
have 16 examples, and they're saying, okay, 16 examples is where it kind of hits the peak, and it's probably too much. Is
no, no,
is that
no,
what it is?
no. So the GSM 8K has like a couple of hundred or thousand math problems in it. And what's happening is if you give it one chance to generate, it's going to get around 84%. If you give it give it two shots to generate, it's going to increase to around 87%. But then if you keep going to 16 chances to generate a good answer, it's then going to get somewhere like 90 to 91%.
Does it keep the memory on the each subsequent tries? Does it keep the context or no?
Yeah, so with best of n sampling, you generate 16 responses, and then you
Okay,
ask,
so it's stateless. Okay.
yeah, and then after you generate the 16 responses, you then give it to some ranker that then chooses the best model out of that.
Right.
The
Okay,
problem,
so
yeah,
I fail to see the innovation in here, like because we know that you give something a system try 16 times, that there is some inconsistencies between responses, so trying 16 times is not as crazy as it seems in other cases, and then you pick the best result out of the 16. Now,
yeah.
what do you think is the actual innovation in this case?
So the best of n sampling is widely used. What this paper I think is trying to introduce is you can get the same performance of generating 16 samples with this like early stopping and then asking the model how well it did and if it could do better again. And so then that's proxying actually generating 16
Right.
samples when you only needed to generate here, which is like 1.6 or something.
Okay. So the assumption is if we can make this scalable, and it may take twice as long to generate once. Okay, I see what it's trying to say. It's basically saying we have the early stopping criteria mid generation, and it's able to detect when it's kind of going off the wrong track,
Yeah.
and then stops early and comes back. And
Yeah.
right, but from an engineering perspective, it's not exactly the most practical, right? You don't really want a 3 second latency turning to 10 by the time you're done, right? You're drastically
I'm not reading that it takes that much longer.
Well, yeah, I think the thing that they want to do is if you bring down if you have enough compute to generate and especially with services like Grok, for example, if you generate 16 responses and you get 91%, and you can already generate at 12,000 or 1,200, I don't know what, like
I'm
12,000.
talking about latency.
I don't think I haven't read anything about latency in this.
So go to the next
Okay.
page though. We saw the bit with the story.
Yeah, this here.
So here you could have, especially on something like write a novel, where it's going to use the whole response context space. You could generate 16 stories and pick the best. Or you can get, what's that, 3 sentences in to a story, give it, add the system prompt, would you do better if you started over, yes or no, generate the one more token to see if you should complete that, or you just kind of
Right.
abandon it and then you go back. So the point is that you save generating the whole
Got it.
response context when you can
Yeah.
identify that the story is bogus.
Okay. Okay. So it's kind of replaces an engineering apparatus where you kind of wrap a system where
Yeah.
I remember what it was trying to do now. Like I've seen approaches where like you have a apparatus and kind of run smaller batches, or you generate smaller chunks and see whether or not it works, and then you go back and you do it in parallel multiple times. And so this essentially removes that all of that engineering, all of that infrastructure to try to make that work. And it's saying if we can natively let the model do all of that, then it'll be better. Okay.
Yeah.
All right. Thanks.
I think that I think if latency does become an issue, then the whole best of n sampling you're probably not going to be doing anyway. That would be my suspicion.
I disagree. I mean, depends on the value, right? Like if each individual response is 1 cent and the business case for it is $1, right? I'm happy to do 16 times. I'm just happy to parallel it,
Yeah.
right?
Yes, I say that not to mean like in every circumstance, but
Right. I get it. Yeah.
I also think that from like Stanford University, a lot of the a lot of the things that seem to be in this are and a lot of the things that seem to be around when it comes to inference time to compute seem to be around like inference time compute being the new paradigm of if you're a business using APIs, you probably wouldn't be using these methods. But if you were OpenAI or Google or Cohere or something, and you needed to create a model that used inference time compute, then these are the methods that you might be using.
Okay, okay, got it. So, oh, sorry. Oh, I was not muted. Okay, so what you're trying to say is, okay, if I'm the backbone provider for ML and I need to provide better cost benefit to my customers, and this could be one way to go about it.
Yes,
All
yes.
right.
Because at the end of the day, if you then don't need to generate 16 samples and you can generate 1.6 or whatever they said before,
Mhm.
you're going to be saving like they said 56% of less tokens. Then that seems to be quite useful economically for you. Yeah.
Okay. It has its business cases.
Yes.
It has its business cases. I think for most people, it probably yeah, it has its business cases, but okay, keep going. Good
I
job.
do one of the things that I think I need to say on this is that like the drop from 16 samples to 1.2 samples the from what they like, it seems like this is a huge drop, as in I wonder what samples they actually used to test to this, because what the 1.2 samples seems to indicate is that the pruning is doing most of the work, and that might indicate some type of cherry-picked data. Like if you're generating something like a really, really difficult math problem or a really, really difficult like English prose or something, you probably find that if the evaluation criteria is a little bit more gray, then you wouldn't be able to do pruning as easily as you could if you just generated the entire sampling. That would be my
I
suspicion.
think
I'm not
I
really
think that
sure.
comes back to the idea that the models are apparently better at reading than writing.
That's true. Yeah. Um, I will continue, and we'll see where this goes. Um, Our approach allows for more efficient and scalable use of compute resources during inference by enabling models to dynamically allocate compute during inference based on task complexity and the model's capability. We optimize resource usage, ensuring efficiency in processing all types of prompts and tasks. This adaptability makes using inference time compute far more practical and ready for the real world where LLMs are used for a wide variety of applications. Preliminaries and notation. An autoregressive language model generates a sequence Y, being Y1, Y2 to YT, given an input context X, by predicting tokens sequentially. Assuming the model is parameterized by theta, the conditional probability distribution of generating a sequence Y given context X is the p theta of Y given X. So that's our output given our input context is equal to t equals 1 of the sigma. Is that sigma? I can't remember.
Product.
What?
Product.
Product. Of t equals 1 to t. What's the Greek character though? What do you call that?
Isn't that a capital pi? I'm not totally sure.
T
think
equals 1 to t of our probably p theta of y t. So that's our yth token given x, and y being less than t. So this is saying the probability of the yth token given our input context and all of the tokens that come before that y, and we're multiplying all of the probabilities, and that's going to give us the probability of the entire
output given the input.
Yeah. With a given convention y less than t equals this. For ease of notation, we defined y, p theta yt given x being equal to the p theta probability theta of yt given yt and x. For vocabulary size m, the probability of predicting the tth token yt is determined using softmax with temperature that one on logit score z for all the tokens. P what's that? I'm blanking because I'm being recorded, but what's this one again? That's
I think it's a lowercase gamma.
Yes, it is gamma. The probability of the p theta of yt given x is equal to the exponential of z sub t divided by gamma on the sum divided by the sum of I equals 1 to m of the exponential of zi divided by gamma, where zt is equal to the logit theta of yt given x and y less than t. So all of the tokens before. Higher values of gamma introduce more randomness. As the temperature gamma approaches 0, the distribution becomes concentrated on the token with the highest logit.
That's just standard temperature, right?
Yes, yeah, this is the preliminaries and notation section. So I'm just going through that. Next, token prediction is a typical approach used for pre-training and fine-tuning of LLMs. In particular, supervised fine-tuning minimizes the cross-entropy loss between the model's predicted next token and the target token in a given sequence. Given a dataset D equals XY, the set of XY of an input context X and target response Y, the supervised fine-tuning loss is given by the loss function of theta given the dataset is equal to the negative expected loss of X and Y of the dataset of the sum of t being equal to 1 to the absolute value of.
I don't think it's the absolute value. I think it's the length of the response.
Okay.
So
length
it's that sigma notation there is just saying the loss is the sum of all the individual predictions of tokens in the output text.
Okay. Because we're taking the log probability of the output token given the input and y to that, and we're then summing up all we're summing up all the probabilities, which is the same as doing the product, and that's the log probability. So then that's going to be the expected loss for the entire thing given target response. Yeah, so right. So
the whole log loss thing always struck me as just being done to be mathematical. Well, It's like it's unnecessary to explain it, but it makes it a lot more convenient to build it. The biggest issue is that these probabilities are so small that they don't fit in 64-bit floating points. So you can, if you can get the log loss, then you just get some negative number. You can get very, very small.
Right, and so that's the reason why we take the log loss is because the negative floating points eventually underflow, and then you don't get anything.
Yeah.
That makes sense. On policy, pairwise preference dataset is a preference dataset that consists of responses generated by a single model. D preference is equal to the set of X, Y1, Y2, and L of I if I equals 1 to N.
Is that the 16 observations thing that we were talking about before?
The whereabouts.
The preference data set. Is that what that means? But it has Y1, Y2. Or
Yeah,
just...
so Y1, Y2 is so you're given a prompt, and then you're given two different responses.
But are those subs the substrings for tokens within the responses, or are those whole responses?
No, so Y1 and Y2 are two, so you're you're given two separate responses to a prompt, and then L, I guess, is the preference on those responses, and that's the preference data set.
The only difference in notation being that it's bold, but
yes, that is a very good point. They say the reason this one here is target response Y. This one here is IT. I'm not sure. Maybe that's a thing that I haven't come across before or something. And then
but that's just talking about that preference data set. That's the whole point about, like, originally when it's best of n, you're generating 16 completions for whatever the prompt is. Is that what they're talking about here?
No, but so the reward model usually, when it comes to this number that before this system this method is generated, it's not talking about generating 16 different things. It's talking about how you train the reward model to start with. And using pairwise, so having one response and then one input context, so one prompt and two responses. If you have enough of them, you can then start to build a model that is good at doing that for every single thing. So it gives a reward model to everything. The 16 generation things I think are different currently.
Okay, let's keep going.
Okay. Where X is the input and Y2, Y1 are the two responses generated by the model, and L is the preference label that indicates the outcome of the comparison between Y1 and Y2. L is equal to 1 if Y1 resulted in a win and Y2 resulted in a loss. 0 if Y1 and Y2 resulted in a tie. -1 if Y1 resulted in a loss and Y2 resulted in a win. To simplify our analysis, we assume that the preference labels L are based on the underlying reward function R, X, Y, and a threshold epsilon that defines if one completion is more preferred. L is equal to 1 if R, X, Y1 minus X, Y2 is greater than epsilon. 0 if the absolute value of those two are less than or equal to epsilon, and -1 if that 1 minus 2 is less than negative epsilon. So we're giving it so given the reward function, you're given it a threshold that you're basically rounding it to, it needs to be bigger than epsilon for the label to preference one over the other, which makes sense. Because if you have two that are very, very similar, and it would be 0. You don't want to be given 1 to another. Like you don't want to reward something that is very, very similar to the other one. So you just give it a label of 0. Bradley Terry BT reward models consist of a base model theta B and a shallow MLP reward head theta R. They predict a scalar reward score R hat of R sub theta B and theta R of X comma Y given an input and response. They are initialized from pre-trained base model and randomly initialized reward head, then trained on a data set of n examples, D of the set of X, Y win and Y loss of I from of I equals 1 to n, where Y win is the preferred response and Y loss is the dispreferred response. They are trained to predict a higher reward for the Y win than for the Y loss under the Bradley-Terry model. This is achieved by minimizing LRM, which is the, I guess, the Bradley or the loss function of theta B and theta R of D, the expected loss between X and Y loss and Y win on the data set is log of that
Isn't that sigma?
sigma, log of sigma of R theta B R theta R of X Y win minus R theta B.
That whole thing's reward function. So log of sigma of reward function of the winner minus the reward function of the loser.
Okay, gotcha. So we're minimizing the expected loss for yeah, we're minimizing the expected loss of win minus loss. That yeah. They are trained to predict a higher reward for Y win than Y loss under the Bradley-Terry model. This is achieved by minimizing that. I'm just trying to get my head around. So base model is a theta B.
Yeah, so base model, that's
But NLP
LLM.
reward head is
And then NLP, that's just another new model that's tacked onto it. So it takes in the same input. The output is then so the input is X, the output is Y plus a reward head theta R. So that's why there's 2 outputs. The B base output that is Y plus the reward output
okay.
that is the score, and it's just a scalar.
Gotcha. So we're getting the reward of the base model and then the reward head. Right.
Yeah.
So basically training, we've got a model that is is this the model that is the reward head? And then
So when they say base model, that's some existing LLM.
yeah.
And so they took the neural net structure and they tacked on an extra scalar that was randomly initialized reward head. And then they trained that, optimizing the reward head to minimize this error function 2.7.
And I guess the reason why this is that, so you want the reward head to be the part that's activating.
Yeah, I think they used the reward head to get the scores in 2.6.
Right. Okay. So the shallow MLP reward head is a head that's attached to the original model, right? Is that
Yeah,
sort of
that's what I'm reading.
gotcha? And so then you want the output of the MLP reward head to then be the thing that's activated when you're asking the model, could you do better? And then it would this part here would be the part that's activating, that's then giving the number that is minimized by this here, which you're then trying to predict.
Yeah, so the data set used to train the reward head is that D equals X, Y win, Y loss. And there's N of those in that data set.
Okay.
So the reward head is just trained to give a higher value on the win given X
Yeah.
than on the Y and the X and loss.
Yeah. That makes sense. Okay.
I don't think we went over where they use that L from 2.6, but this Bradley Terry part is just explaining, and this is from 1952. It's just explaining how they got the reward that they use in L.
Yeah, okay. Interesting. Um Best of N Snell et al. 2024 is a widely used test time compute approach to improve the performance of LLMs. Specifically, given a prompt, N candidate responses of an LLM are scored using a reward model, and the highest scoring response is filtered as the final response. 3. Adaptive inference time compute via capability aware and mid-generation self-evaluations. In a simple yet effective method for allocating of test time compute is best of N, allowing for the model to improve upon its responses over greedy sampling. However, the generation of large fixed number of samples is computationally expensive, and the efficacy of this approach relies heavily on the quality of an external reward model, which can additionally incur substantial computation costs. In the following section, we address the cost of robustness of the reward model by establishing a general framework for self-evaluation via token prediction. We show how to train capability aware and mid-generation self-evaluators to reduce the cost of generating a large fixed number of samples. Capability aware and mid-generation self-evaluations. In the classic reward modeling paradigm, a pre-trained LLM is used as an initialization for reward modeling. However, this approach also relies on newly added reward head to output the reward, which diverges from the token prediction task for which the LLM was trained, which can hurt performance for reward modeling. Additionally, general preference-based reward modeling learns only to rank arbitrary responses. This may be limiting for comparing on-policy samples, such as those from best of N, during inference to determine how good the response is with respect to the model's own capabilities. Furthermore, reward models are generally only able to evaluate full responses. Responses that are clearly unpromising very early on in generation still have to be generated until the model end for evaluation, wasting computational resources. Can we use an alternate paradigm to model rewards to address these limitations? I'm assuming that they're going to say yes.
I think that's the part of the paper, yeah.
We propose capability-aware and mid-generation self-evaluations, a paradigm in which we query the reward model to predict the probability of restarting generation will not yield a better response. This probability can be used to elicit adaptive test time computation, where the model can dynamically allocate compute dependent on the difficulty of a query and its own capability. This is because to decide whether or not to allocate more compute to a given query, we need to know if it is fruitful to do so. For example, for easy queries, the model may have already outputted the best response it can, so resampling is unnecessary. Additionally, for difficult queries, sampling more may lead to a minor improvement in performance, leading to unfruitful resampling. We illustrate this paradigm in figure 2. Modeling, which one's that? That one, we already went through that. Modeling this probability effectively has 3 components. 1, reward modeling using token prediction to better leverage the pre-trained models' existing knowledge and capabilities. 2, relying on on-policy pairwise preferences and ties to model the probability that the model cannot generate a more preferred response. And 3, using truncated responses to model the probability that restarting generation will not yield a more preferred response. Traditional reward models can suffer at this task as they are model agnostic. Through these models, though these models can rank how different responses perform for a given task, they are unable to quantify effectively how effective resampling would be, not capability aware. Furthermore, a desirable property of a reward model is to early stop the generation of samples that are not promising in order to give the model another chance without wasting compute. Reward modeling with token prediction. To obtain a self-evaluation of a response from an LLM, we simply append a predefined self-evaluation token I to the generated response Y and obtain a score in the form of likelihood of a predefined token at T good, corresponding with the likelihood of the response being good. This approach allows us to acquire rewards without any external reward model, making it highly cost-effective as we can reuse the KV cache obtained during the generation of the response. Also, this leverages the existing zero-shot capabilities of the model to judge its own responses as a prior, which has been shown to be effective in works such as Madden et al. 2023. Formally, given the preference dataset dpref x, y of the set of x, y good, and y bad, which contains input context x and response pairs y, we can train the self-evaluation model by maximizing the likelihood of the good token log of P theta T good given X and Y good for good responses Y good, and the likelihood of the bad token log P theta T bad given X and Y bad for the responses Y bad. To achieve this, we minimize the supervised fine-tuning loss in equation 2.3 on a modified variant of the preference dataset D evaluation. D self-evaluation. D self-evaluation is equal to the set of X, Y good, and I paired with T good in the union of X, Y bad, and I paired with T bad. So you're given
So X is the
prompts.
input.
Y is the good example. I
Yeah.
is prompt. I is the self-evaluation prompt, and T
Yeah.
is the good token.
Right.
And this is the same, but with the bad example and the bad token. During inference, we normalize the likelihood of T good as the score to rank responses. Score is equal to the P theta of T good given X, Y, and I over T, the sum of T being an element of T good and T bad of P theta T given X, Y, and I.
Yeah.
So,
So that's what I was talking about with the grammar.
right.
They take the score. It's just the score of good divided by the score of good plus score of bad.
Uh, okay. Yeah. That makes sense. So where we are, it is token based. Like the token based probability here is we're exploiting token loss to get our score, which is cool.
So do they build this data set to just I think we're gonna get into how they train it because I'm
Yeah. Let's see. How many pages do we have left? 5. Wow. Oh, most of them are references. Never mind. Given that a language model has a fixed vocab size V, probability mass can be spuriously assigned to tokens T not equal to T good and T bad, resulting in this normalization not to be desirable. Note, it is beneficial to establish within the self-evaluation prompt that the LLM has to perform a classification task that the target tokens are natural responses to effectively leverage the zero-shot capability of the model. We find that poorly designed self-evaluation prompt the model will overgeneralize during training and respond with T good or T bad for all queries regardless of relevance. We need to keep the underlying policy or model unchanged when learning to self-evaluate. To do so, we need the model's prior distribution of tokens to be similar to what we expect after training, where P theta of T good union T bad given X, Y, I is almost equal to 1, approximates 1.
So this is different than what I was thinking with the grammars. So they're not constraining the grammar. They're just asking it to say good or bad.
Yeah. Yeah. But I guess the thing that you're doing is like you're only calculating the score on the probability of good or bad anyway. So this is technically token generation because you don't care what it outputs because you're taking the probability of the token anyway.
Yeah.
Which can token as I understand, I haven't looked into it a whole bunch, but with grammar constraint generation, you're doing a similar thing where you're getting the logic probabilities and you're removing all of the ones that you don't want, and then you're just sampling from the ones that you do want. I think. I'm not completely sure. Anyway, I will continue. Where are we up to? The probability that the model cannot generate a more preferred response can be easily derived from on-policy pairwise preference and ties. It is the probability that the current sample Y results in a win or tie against another sample Y prime. More formally, P of Y prime. What's this? Do you know how to pronounce this?
Probability of
Y prime approximating of Y X. Yes.
the of Y.
Is equal to the reward
Go
model.
back to the prior sentence on the last page.
Oh wait. On policy pairwise preference ties, it is the probability that the current sample Y results in a win or tie against another sample Y prime.
Result the probability.
Probably over the probability over Y sampled from the model's distribution, P theta of Y given X of Rx, the reward model for the current response Y given input X, and minus R of X of Y prime is the reward model for an alternate response Y given the sample input X. Epsilon is a small threshold value is equal to the probability that the difference in the rewards is greater than the or equal to negative epsilon. Okay, that makes sense. So we're getting the probability of a win or a tie. It shows that the probability of the current response Y is being not significantly worse than a randomly sampled alternative Y prime is equivalent to the probability of the current response resulting in a win or a tie. This allows the model to estimate how likely it is that generating a new response would not yield in a better response. Okay, that makes sense. So where this is used to make sure that probability of win or tie is not going to happen.
So they're taking a whole bunch. So for a given X, they're taking a whole bunch of candidate Ys.
Yeah.
And so it's a probability. What do they do with the probability? I think
I think they might.
I think this makes more sense when they get into it.
Yeah. Accounting for ties in reward modeling is especially important for on-policy pairwise data, where responses coming from the same model are very unlikely to be similar.
Likely.
Sorry?
They're very likely to be similar. Not, you said unlikely.
Oh, whoops. Very likely to be similar. Ties commonly occur when generating responses from the same part model, e.g. 40% of the time, and are even more common with simple tasks. Since less ties indicate that the model cannot do better, they are crucial when learning to do capability-aware self-evaluations. If ties are not specified, it is also harder to model the reward as the model has to distinguish between extremely similar responses. Furthermore, since 100 minus 40 divided by 2 is 30% of samples result in a loss, we can see that the model can do significantly better on a query only roughly 30% of the time.
I think it depends on what your epsilon is.
Yeah, I think that's why they have, that's what this part is, that they're trying to, yeah, trying to figure out how to not need to generate if you think that it might be close. If that makes sense. Maybe, does that even make sense to me? I'm not sure. Notice that P win in union with tie given XY monotomically increases with the sample's underlying reward RXY. This means that it can also be used to determine if one sample has a higher reward than another. Since inference-time compute strategies only care about being able to rank responses, it turns out that modeling P win in union with tie given X and Y is more useful than the reward model of X than Y, since it can be used to inform decisions on whether or not to allocate more compute. That is interesting.
Yeah.
That is, yeah, that's really cool.
But yeah, I mean, it might be more useful, but you still need to calculate R of X and Y. So it's just a further calculation.
Yeah,
Unless-
well,
unless
yeah,
they have some-
that's just saying that it's this here is more useful than this part here.
Yeah. But they're just doing the comparison with the epsilon.
Well,
The hard part is getting R of X and Y.
but that's why I think that's why if you model it, so you're not getting it exactly, but you're trying to get this so that you're guessing this.
Yeah.
And then once you guess that, it means that you don't actually need to calculate everything.
But so do they actually calculate P of win and union tie without calculating the individual rewards?
Um,
I think we'll get to that.
yeah. The probability that restarting generation will not yield a more preferred response can be used to evaluate the quality of the partial response y of 1 colon t in the context of adaptive inference-time compute. If we find that this probability is low, we can stop spending additional inference resource on generating the remainder of the partial response, pruning poor partial responses. Again, in the context of unpolicy pairwise preference or ties, this probability is simply p-win union tie, conditioned on a partial response y of 1 to t. So this is probability of an y prime sampled from the probability of y given x of this here, but we're only using y to 1 to t, which is pretty nifty, honestly. And I think we're just modeling it. So the whole point of the thing with the tokens and everything is that you don't actually need to calculate this every time. Modeling these probabilities with an unpolicy pairwise preference data set with ties. To train LLMs to make capability-aware self-evaluations, we construct a data set derived from an unpolicy pairwise preference data set with ties, where good responses are those that resulted in a win or a tie, y win, y tie, and a bad response are those that resulted in loss, y loss. To train LLMs to make capability-aware self-evaluations mid-generation, we simply include the same examples, but with responses randomly truncated. Y win trunk, Y tie trunk, Y loss trunk. We use the following self-evaluation prompts and target tokens. Would it be better if you started over yes, no, T good equals no, T bad equals yes? Our final data set, D capability aware, used to minimize supervised fine-tuning loss, equation 2.3 is constructed as D capability aware is equal to the set of X, Y win, I paired with T good, and Y tie I good union with loss bad, and that all in union with X, Y win truncated, I T good, paired with T good, and tie Ted paired with good, and loss truncated paired with bad. During inference, we compute the normalized likelihood of the T good no token to score full or partial responses. During inference,
Why they have
compute.
tuples and within the tuples.
Yeah, that's these ones here.
Yeah, I mean, it makes sense what they're doing. They're just taking a string that is the sequence of token that's the original input, the sequence of token that is the winning output, the sequence of tokens that is their self-evaluation prompt. Would you do better if you started over?
Yeah.
Yes or no afterwards.
Um.
But I guess they're only training it to output yes or no.
Yeah, but the thing that you're minimizing isn't like in standard next token generation, you're trying to minimize the loss between one token and the expected token to 0. In this one, you're trying to reduce the loss between the two tokens, not to 0, but to the score that you expect it to be.
I think so.
You don't, oh, really?
I think they're still training it the same way, but where the input text is X, Y, I, and they're training it to predict one token, yes or no. In the same classical training. It's just a creative data set that they built.
Okay. So here we've got P win union tie X to X, Y 1 to T is being equal to the probability of T good given X, Y 1 to T of an I divided by the sum of T being an element of T good, T bad, of the, so the sum of the probability of T given X, Y 1 to T and I and takeaways for capability aware and mid-generation self-evaluation.
Before, go back to that probability function. That is essentially the same probability function that they explained in the background work. If you go back a page,
Yeah, okay.
back
Here.
again.
Is this one here, isn't it?
No, go back again. 2, 2.
Yeah.
It's the same as that. The difference being that they've limited the tokens to the word yes or the word no.
Yeah. So I guess to your point, they are basically doing constraint generation.
At least in calculating the probabilities.
Yeah.
I think they said that they didn't have to constrain it because of how they constructed the self-evaluation prompt.
Yeah. Through traditional reward models, takeaways for capability aware and mid-generation self-evaluations. Through traditional reward models, though traditional reward models can rank samples from a model effectively, they cannot quantify how much better a model can do if it resamples. We introduce capability aware self-evaluation, which allows a model to model the probability that it cannot generate a more preferred response. This consists of three components. One, reward modeling using token prediction to better leverage the pre-trained model's existing knowledge and capabilities. Two, relying on on-policy pairwise preferences and ties to model the probability that the model cannot generate a more preferred response. And three, using truncated responses to model the probability that restarting generation will not yield a more preferred response to consider the efficacy of partial completions. We will now explore how these techniques can be used to make best of n more efficient and scalable. Making best of n efficient and scalable. Best of n is not very computationally Best of n is very computationally expensive as it requires the generation of large fixed number of samples. This can lead to wasted computation on queries that do not require more compute and underutilization of compute on queries that could benefit from it. To remedy this and make best of n more practical, we introduced two primitives that leverage the capability aware and mid-generation self-evaluations that we introduced in the last section. The first is adaptive sampling, where additional samples are allocated to a query only if they are predicted to be beneficial. The second is early pruning, where unpromising samples stops from being generated further to save inference computation. Adaptive sampling and annealing. We introduce adaptive sampling as a technique to allocate inference time compute only when it is beneficial to do so. We further introduce exponentially increasing parallel sampling to mitigate the main disadvantage of adaptive sampling, latency. Finally, we introduce the temperature annealing strategy to balance exploration and exploitation while adaptively sampling and boost efficiency. Resampling until meeting a threshold. We adaptively sample by resampling only when the model predicts it can produce a better response. We do so by computing the likelihood that the model cannot generate a better response, p win union tie given x and y for every sample. If this probability exceeds a predefined threshold tau for any sample, we stop resampling and select the sample with the highest p win union tie given xy as the final response. Otherwise, we resample, repeating this process until the threshold is met or a maximum number of samples n max is reached. This approach concentrates computational resources on prompts where improvements is likely, avoiding unnecessarily sampling when further gains are improbable, increasing number of parallel samples exponentially. To reduce latency, we sample in exponentially increasing batch sizes, specifically for kth sampling iteration. The batch size nk is defined as n1 equals 1, nk equals 2 to the k minus 2 for k is greater than 1. This ensures that cumulative number of samples in the kth iteration is k 2 to the k minus 1. This exponential increase minimizes latency, reducing the number of iterations needed to meet Nmax while allowing for enough self-evaluations to determine if larger batches of samples are necessary. Temperature annealing schedule based on number of samples generated so far. To balance exploitation and exploration, we vary the temperature gamma. The temperature for the kth iteration is given by gamma k is equal to 1 minus 2 to the negative k minus 1. So we've got resampling until we meet a threshold and increasing the number of parallel samples. So we're essentially like growing a tree, which is going down the and we're also we're going down a tree and we're adjusting the types of the way that we're traversing down it using temperature and pruning things that we want to prune. And the batch size. Okay, so the more
I guess the iterations are 1 indexed.
that's a good point.
Because for 0,
Yeah.
the temperature becomes -1. It doesn't seem right. But for iteration,
we've got
for iteration 1, I'm looking at 3.8. For iteration 1, you have 2 to the 1 minus 2 to the 0, which is 0. I don't know how does temperature 0 work? Is it? Oh, I guess that's just taking the most likely one without any sampling. That would be temperature 0. And then from there, the temperature gets higher.
for the case,
more of them?
temperature is equal to 1 minus 2 to the negative k minus 1. So what is this? What does that look like on a graph?
To the exponent minus put an x instead of k.
So we increase at the first iteration.
Okay, so yeah, what is
where
temperature 0 would be selecting
-1. But
well,
then
that's why I think it's 1 indexed, because -1 temperature doesn't make sense as far as I can
well
tell.
no, but it yeah, that's true.
So the first is just try to take the most likely, then you get your temperature that's closer to what's that 0.5.
And then when you're right, and then we approach 1.
Yeah. And then
we approach 1 because then you don't want the temperature going up infinitely.
Yeah. So the temperature at 1 is when you get the most random creative responses, right?
Yeah.
And then temperature 0 is just strictly the most likely. So the temperature gets higher as you're doing more samples, which is also pretty logical.
That makes sense because like you're branching out from the most probable least likely temperature, and
It'd be
then
interesting to see if they tried other annealing algorithms, because they're just cutting the temperature in half each time. No, not the strict.
they're increasing the temperature until it gets to 1. and that should get happening.
Yeah. The distance from one is cutting in half each time.
Yeah. I will continue. Algorithm 1, adaptive sampling and annealing. Require input prompt X, maximum samples N max, and threshold T. Initialize K to be 1 and N cumulative to be 0 and S to be the empty set. Well, N cumulative is less than N max. Do NK
Is one.
is 1 if K equals 1, else K else 2 to the K minus 2, and N cumulative is N cumulative plus NK. Gamma K is 1 minus 2 to the negative K minus 1. Sample NK responses of the set yi from I equals 1 to K using temperature gamma K. For each yi in the set yi I equals 1 to NK, do compute P is P of sub I is P of theta when in union with tie given X and yi, add yi pi to the S and end 4. So here we are
S is
generating
your set of completions, right?
S is the set of completions. Pi is the set of
It's the PI is the probability
right
that
of
YI is a winner at tie.
yeah, and then we're doing that for everything in our. We're doing that for the number of the number of parallel computations in the current response. So this is the parallelized bit.
Yeah.
And if any pi is greater than tau, then break. And if and k is k plus 1, and then we go that, and then we end that. Select y star from S with highest p sub I, and return y star. Initially temperature starts low, e.g. Gamma 1 equals 0 to prioritize high probability responses. As K increases, gamma K quickly approaches 1, encouraging more diverse and creative sampling. This annealing schedule allows for models to first focus on exploiting the most likely responses and then explore alternative options as more samples are generated. Early pruning of unpromising samples. One downside to adaptive sampling requires generation of samples in series, which introduce latency. However, can we still leverage parallel sampling to avoid increasing the latency of response generation, but still enable adaptive test time compute allocation? One approach to reducing computational cost in parallel generation is to early prune unpromising samples based on mid-generation self-evaluations. When to prune. Pruning too early risks discarding samples that could improve, while pruning too late offers minimal savings. Thus, we balance this trade-off while selecting the fixed number of initial tokens, e.g. 64 or 128, before making any pruning decisions. Which samples to prune? After generating an initial number of tokens, we compute the intermediate self-evaluations for each partially generated sample. After ranking samples by the resulting scores, we stop the generation of the bottom X percentage, e.g. 50% or 75%, to conserve computation. This ensures that only the most promising partial samples continue to be generated. Takeaways for scaling best of N. We discussed 2 strategies to efficiently scale best of N leveraging capability aware and mid-generation self-evaluation. 1, adaptive sampling and annealing, and 2, early pruning of unpromising samples. For adapting sampling, we allocate inference-time compute dynamically by exponentially increasing the numbers of samples for best of N. This allows us to increase the number of samples for more difficult queries, while saving samples on easier intractable queries. Early pruning takes an alternative approach where a larger sample budget is initially used to sample a fixed number of tokens, e.g. 128 or 256, at which point mid-generation a self-evaluation is done, where the least promising samples are pruned to conserve computation. Table 1, best of 16 performance on AlpacaEval win rate versus GPT 4% and GSM 8K%, using capability-aware self-evaluation token prediction. LLM as a judge, which also used token prediction, but without fine-tuning. The commonly used Bradley-Terry external reward model and the underlying reward model are used to create our experimental preference data. So we've got random one sample capability aware is the best. Our zero shot LLM as a judge is somewhat better than our random sample, our underlying reward model. So we're sort of approximating this with like this capability where probability when you tie is trying to approximate the underlying thing. Does that make sense? Is that a correct interpretation? Anyway, I'll continue.
Did they mention which model they based it on?
8 GPT, no, not what was it? Llama 3.1 8B. Yeah. Which is why the AlpacaEval is so low, because it's using an 8B model. Actually, to be fair, that is pretty high for an 8B model, I would say. Experiments. We evaluate our methods by first examining the sample efficiency of self-evaluation. We then evaluate its impact on optimizing inference-time compute with adaptive sampling and early pruning of unpromising samples. Training data and evaluations. Construction of on-policy pairwise preference with a data set with ties. Training a reward models typically requires human-labeled preferences, which are costly to obtain, especially for on-policy data generation by the model being trained. To mitigate this, we utilize an existing reward model, our ARMO RM, Wang et al. 2024, trained on approximately 1 million preferences. This reward model serves as our underlying reward, R, X, and Y. We conduct our experiments using the Llama 3.1 8B instruct model, which is fine-tuned on preference data set of 50,000 real user prompts from LMSYS, and pairs of on-policy responses sampled from the same Llama 3.1 8B instruct model. These responses are scored using ARMO RM, the underlying reward. Preferences or ties between the responses are determined using a threshold epsilon of 0.01 on the reward differences, resulting in an on-policy pairwise preference dataset with approximately 40% of ties. Evaluation protocol. We evaluate the performance of our self-evaluation model and adaptive test time compute approaches in 2 domains, the AlpacaEval benchmarks and the GSM8K dataset. AlpacaEval 2.0 is an automatic benchmark that compares model responses to those generated by GPT-4 across approximately 800 representative prompts. The final metric is the win rate against GPT-4, adjusted to increase correlation with human preferences, Spearman correlation of 0.98, while highly correlated with human judgments. This metric is relative. It measures the success based on outperforming another model rather than achieving absolute human satisfaction. GSM8K is a collection of 8.5K grade school math word problems involving multi-step reasoning and basic arithmetic operations. We use GSM8K as it is a popular benchmark for reasoning as well as absolute measure of performance that is not relative to another LLM. This is particularly useful in evaluating adaptive sampling where it allocates compute resources to queries that benefit from it. Performance and sampling efficiency. Baselines. To evaluate performance with best of n, we use 2 baselines. The zero-shot LLM as a judge baseline using Llama 3.1 8B instruct without additional training, we prompt and get scores for zero-shot predictions in the exact same manner as we do for capability or aware self-evaluations. The Bradley-Terry reward model also uses Llama 3.18b instruct as the base model, and it is trained using the same on-policy pairwise preference dataset with ties. As shown in Table 1, the zero-shot approach performs modestly on both benchmarks, confirming that LLMs have a non-trivial ability to self-evaluate. The Bradley-Terry reward model unsurprisingly does much better. Our token prediction method outperforms both. On AlpacaEval, it achieves a 33.8% win rate against GPT-4 using best of 16 sampling, slightly surpassing the Bradley-Terry model's 33.2% and nearing the underlying reward model's 36.3%, trained on 1 million preferences. On GSM-8K, token prediction attains 91% accuracy, significantly outfalling the Bradley-Terry's model at 87.7%. This suggests that our method is more sample efficient and generalizes better, especially on queries that might be uncommon among real user prompts like those in GSM-8K.
So are these performance adjusted metrics, or are they just about how good they are at answering the question?
What do you mean by performance adjusted? As in,
like now they're just talking about how good they are at matching the user preferences or answering the 8th grade questions, right?
yes.
And so they're saying is that these approaches are better, and we're not even getting to the fact that they're cheaper, right?
I think so. So currently we're just talking about the scores on the so on AlpacaEval, we're doing a 33.8% win rate against that using best of 16 sampling. And we're just changing the type of sampling. And the underlying reward model
Yeah.
I don't think these are performance adjusted.
No, I think they get into that. I see a little bit of that on the next page, so I think that comes later.
On GSM-8K, that makes sense. These results demonstrate that token prediction effectively leverages the pre-trained models prior for self-evaluation, approaching and the performance of the larger Llama 3.170b, which achieves 38.1% on AlpacaEval and 95.1% on GSM-8K. With additional data and hyperparameter tuning, we anticipate that we can easily further close the gap with the underlying reward. We also examined the other probabilities to model with the token prediction, specifically p theta win or p theta win given not tie. Our findings, as shown in Table 3, indicate that including or removing ties does not significantly impact performance, but modeling p theta win is significantly more difficult as it forces the model to distinguish between the samples that result in wins or ties, which are both cases in which the model performs relatively well for its capability.
I wonder if they considered multiple epsilons. Like their epsilon was 1%, but maybe like 0.1% would be different.
Maybe that'll be in the further study or aberrations or something. Because that does seem quite arbitrary, doesn't it? Notably, using best of n sampling with our methods allows the Llama 3.18b model to approach the performance of Llama 3.170b, a model roughly 10 times larger that gets 38.1% and 95.1% respectively. This highlights the efficacy of best event sampling in enhancing the model performance. In the following section, we address the expensive nature of this method with adaptive compute strategies. Efficiency and scaling of adaptive sampling and annealing. We evaluate the efficiency gains and performance trade-offs of our adaptive sampling and annealing strategy in the GSM-8K dataset. Our objective is to retrain the performance benefits of best of 16 sampling while significantly reducing the average number of samples used and minimizing latency. We want to evaluate the method's ability to allocate samples when necessary. For our experiments, the capability-aware self-evaluations are always used to select the best sample. This is so that the final selection method is not a confounding factor. We want to evaluate the method's ability to allocate samples when necessary. For our experiments, the capability-aware self-evaluations are always used in the best sample. This is so that the final selection method is not a confounding factor. As a baseline, we first assess the performance of best of n. This best sample is selected using self-evaluation, which with token prediction. Figure 1 shows that an increasing the number of samples from 1 to 16 incrementally improves the GSM-8K pass at 1 accuracy from 84.2% to 91.0%. This represents the maximum achievable performance with our method, which we define as 100% of the maximum improvement. However, getting a fixed large number of samples per query is expensive. To mitigate this, we introduce adaptive sampling controlled by a threshold tau and a maximum number of samples n max. Initially, we test adaptive sampling using the underlying reward model to decide whether to generate the additional samples. As shown in figure 1, this approach does not significantly outperform random selection. While the underlying reward model effectively ranks responses, it does not consider the model's capability to improve upon its own outputs, substantially limiting its effectiveness in informing resampling decisions. In contrast, our adaptive sampling method uses capability-aware self-evaluations via token prediction yields substantial efficiency gains. Table 4 demonstrates that adjusting the threshold t for the win or tie probability, p theta win union tie x given xy, we can control the average number of samples. For instance, setting t to 0.98 results in 97.1% of the maximum performance while using only an average of 4.1 samples compared to the 16 samples required for maximum performance. Moreover, incorporating the annealing schedule further enhances performance, particularly at lowering thresholds. As illustrated in Table 2, with annealing, we can achieve 73.5% of maximum improvement using an average of just 1.2 samples when t is 0.92. This indicates that our annealing strategy effectively balances exploitation and exploration using sampling. Our adaptive sampling approach offers significant compute savings compared to best of n by adjusting tau and n max. We can fine-tune the trade-off between performance and efficiency. The latency introduced by adaptive sampling is minimal due to the exponentially increasing batch size. That's cool. Efficiency gains of pruning unpromising samples. We evaluate the efficiency gains from early pruning of unpromising samples on the AlpacaEval benchmark. We begin with 16 samples and prune from them. Our primary metrics are the percent of maximum improvement achieved and the number of tokens generated per prompt. The latter is the more accurate measure of computational cost than the number of full samples generated, as partial responses also consume computational resources. Our experiment controlled 2 variables, the number of tokens generated before making pruning decisions, 64 or 128, and the percentage of samples pruned, e.g. pruning 75%. Again, the capability-aware self-evaluations are used as the final sample selection method. Impact of evaluation timing on performance. As shown in Figure 1, pruning at 64 tokens improves performance over random pruning at 0%, 0 tokens. For instance, pruning 50% of samples at 64 tokens achieves a win rate of 33.4%, closely approaching the maximum 33.8% without pruning. The timing of when we perform self-evaluation significantly affects performance. Pruning at 128 tokens yields even better results. Pruning at 75% of tokens at 108 tokens. Pruning 75% of samples at 128 tokens attains a win rate of 33.2%, nearly matching the maximum performance without pruning. This improvement is expected as longer partial responses provide more context for accurate self-evaluation. Overall, there are substantial savings in if one prunes at the right time and the right number of samples.
What does random pruning and 0 tokens mean?
I think I think that's just like you're going to have, let's say you're gonna have 100 generations in the batch. Um, only do like 50 of them or something, or in this case like 75, which I think they're
Switch
doing.
to figure 1.
Sorry. I think the reason why they're doing that is an ablation on if the method of training the token loss and the like yes no probability of stopping is actually working, because if they ended up randomly pruning half of the generations at 0 tokens and randomly pruning it at 64 tokens, you would assume that the downstream performance would be very similar.
I mean, what does prune and 0 tokens means? Like you don't have a generation at that point.
Yes, and I think that's they're making sure that if you're pruning 75% of the tokens at 64 tokens, if you're pruning 75% of the options at 64 tokens, that should be significantly better to make sure that your selection mechanism is working. You want to make sure that that is significantly better than pruning 75% of the tokens at 0 tokens. It's just I think they're just
That
using
doesn't
it
even
as an
sound like pruning. That just sounds like
yes.
getting less samples.
Yes, I think it's an aberration to make sure that the pruning mechanism works.
Okay.
At least that's how I'm reading it. What?
Keep going. Okay, this is the page you just finished.
Yeah. Overall, there are substantial savings if one prunes at the right time at the right number of samples. In terms of computational cost measured by number of tokens, pruning 75% of 16 samples at 128 tokens reduces the average number of tokens generated per prompt from 7,259 to 3,220. As shown in figure 3, resulting in significant performance gains. Thanks. You could have put that into a percentage, but it's fine. Related work. Reward modeling in RLHF. Traditionally, reward models, RMs, within reinforcement learning with human feedback have been trained using discriminative techniques, often drawing on ranking models like the Bradley-Terry framework. These RMs are generally treated as binary classifiers, distinguishing between preferred and dispreferred completions for a given prompt. The preference signal is predicted by generating a continuous score, typically derived from a linear head appended to an autoregressive language model. An alternative line of work departs from this discriminative paradigm by directly modeling preferences through joint probability estimations, as seen in methods that predict the likelihood of one response being preferred over another. Recent advancement in RLHF have been have introduced implicit reward models that can circumvent the necessity of a distinct reward classifier by learning the distribution of preferred and dispreferred completions via objectives like the direct preference optimization DPO and implicit preference optimization IPO. These methods embed preference learning directly into policy optimization process, unlike explicit preference modeling. I haven't gone too far into things like direct preference optimization and implicit preference optimization. So I still need to understand some of that stuff. Another approach to reward modeling is the application of prompting techniques such as LLM as a judge framework, where large language models are prompted to act as evaluators without additional fine-tuning. Despite the potential of these methods, even advanced models like GPT-4o underperform when compared to dedicated RMs in more complex evaluations, such as those found in rewards benchmark. Techniques for inference time compute. During inference, the integration of a reward model with a proposal distribution LLM can be employed to refine the output responses to a given prompt. One notable paradigm in this context is self-consistency, which is designed for factual queries with extractable answers. In this approach, the language model selects the response it generates with the highest frequency across multiple samples. Optimizations such as early stopping self-consistency have been proposed, which terminate the sampling process early if a subset of responses show strong consistently. However, these approaches face limitations due to the dependency on identifying the most consistent response from a large pool of discrete answers, restricting their applicability to tasks like multiple choice or mathematical problem solving. In addition to search algorithms such as best of n and beam search have been explored in works such as Snell et al. 2024, which leverage reward models to select the most promising candidate samples in reasoning tasks. In this work, we examine how to enhance the efficiency of token generation relative to the accuracy of the outputs, with the complexity of query dictating the amount of inference time compute allocation. Furthermore, for multi-step reasoning tasks, this work presupposes that the problem can be decomposed into discrete semantic steps, a potential strong assumption in domains outside of well-structured fields like mathematics. Generative verifiers. Recent concurrent work such as DenRM and Cloud demonstrate that token prediction-based reward models outperforms traditional reward modeling techniques. In this work, we further introduced capability-aware and self-evaluation, which allow a model to understand its own generation capability to enable dynamic allocation of computational resources during test time inference. We also introduced mid-generation self-evaluations that can allow for the pruning of unpromising samples. Discussion, conclusion, and limitations. As language models, LLMs evolve, enhancing response quality through inference time computation becomes critical. Best of n sampling, a traditional approach, generates multiple response candidates and selects the best, but incurs a high computational cost due to its reliance on external reward models and fixed sample sizes. This work introduces a cost-effective alternative, capability-aware self-evaluations performed mid-generation. By appending a self-evaluation prompt to responses, LLMs can predict the likelihood of generating a better response without requiring external reward models. Two adaptive inference time techniques, adaptive sampling and early pruning, are also proposed, allowing LLMs to resample or discard suboptimal responses during generation dynamically. These methods significantly improve efficiency, with fewer samples yielding performance gains similar to a larger set, and early pruning reducing unnecessary computation. Experimental results demonstrate a noticeable improvement in performance across tasks, achieving a 34% win rate against GPT-4 on AlpacaEval with 16 samples, and increasing accuracy on GSM-8K math problems from 84% to 91%. Overall, this approach optimizes inference time compute allocation, making it more scalable and practical for diverse real-world applications. The main limitation of our method is that adaptive sampling introduces latency, which otherwise would not be a problem with only parallel sampling. We minimize this with exponentially increasing batch sizes. We also introduced early pruning to save computation even in parallel sampling. For future work, it may be possible to predetermine the number of samples we need to allocate to a given query based given the query based on the probability that samples would result in a tie. While this would be significantly less efficient than adaptive sampling, it would eliminate latency for adaptive sampling. It may be possible to do different types of search with active capability aware self-evaluations. Beam search or other similar types of search may be possible with general prompts with this new capability. And then we've got references. I think this is really cool, and one of the things that I am wondering about is if they I've been obsessed with the ability to do model steering using the interpretability feature work, because one of the only ways that they're using to get the model to generate different options here is just by increasing the temperature. But if you then have the ability to push the model to generate in a particular like on a particular topic using one of the features that's extracted using the interpretability work, this means that the exploration phase in this is less random, because temperature fundamentally is just sort of just a random process.
Yeah. You could, I think there's a lot of work going on right now about how to sample.
Yeah.
And this, it doesn't change the sampling algorithm. It's still the same thing with the temperature. But the insight is that they're doing it to detect yes and no.
Yeah. Yeah.
I'm curious about what the capability aware data set ended up looking like in real life, and how much training they actually had to dedicate to it.
Yeah, unfortunately they didn't release their public GitHub implementation does not have a public GitHub implementation, which
Are there any other branches?
wait, I just need to thumb up this guy. No, there's one branch.
There's no branches.
Maybe he made it into a different. Oh, look, there's another one. No, it was just that. Maybe there's a different one. No, it's also just that. Yeah, so it would be interesting to see if, I don't know, maybe they'll release it, maybe they won't. But this is cool. I like it. I have not, this is the first paper on inference-time compute that I have read, so I'm not sure how it stacks up.
First paper on which?
Inference-time compute.
Yeah, it's, I like the idea. I think it'd be interesting to see how it looks with different epsilons. And I wonder if you could adapt the number of tokens every time, like as you go, like, right? You know what I mean? So the first, when you have temperature 0 on the first iteration, maybe you let it go all the way. And then the one, when you do 2, you let those go 128 tokens. And then when you do 3, you let those go 64 tokens. So you still get the benefits of the temperature to explore, but you're saving on compute when you're doing more compute on that round?
Yeah, that makes sense.
That would dark.
Wonder I and like for me, I think that the thing that makes me excited about this is the like internal discovery of the distribution of the model. And the token I like the ability to steer it and everything through temperature and everything is doing it like is basically doing like a blind breadth first search without any heuristics. And so that's why I think that doing something like model steering would be adding some heuristic in there and then turning it into a star.
Yeah, it would also be interesting to see on other data sets. I think there's a lot of work to do in these evaluation data sets in the first place and like figure out
Yeah,
a lot of where LLMs really shine is on very subjective stuff. And
that
then having one output preferred over another. Like I see those questions on ChatGPT and I usually pick one over the other mostly for formatting reasons. At least for the kind of questions that I'm asking.
but this is the thing though that like I think that some of it gets interesting when you can hook it up to things that can automatically rank it. Like if you have a Python interpreter that can then run the code and then you wouldn't need the preference pairs and those data sets and everything. And this is the type of thing that I feel like a lot of research papers end up introducing concepts that they use these benchmarks as they use these benchmarks as sort of like proving that the method works and everything. But I think that I feel like the immediate low-hanging fruit when it comes to a lot of AI research is applying them to completely sandboxed environments that then you can just do this and then it can like infinitely get better at the domain when you hook it up right because then it can just learn how to interact with the environment better.
Yeah.
Um, I am not sure if you want to go on any longer. I think that was a good session for the first time. Yeah, that's that.
All right, folks.
I think what's his face left, but yeah.
Yeah, Frank had to run, but I told him thanks for joining. He had some feedback for us that he was going to send later too. So,
Oh, cool.
mm.
Are we still live streaming?